So, now we shall talk about rotational invariance of a system and its relation to angular momentum. That is, if a system has rotational invariance, that is it remains invariant under rotation in space, then the angular momentum is a good quantum number, or rather the angular momentum is conserved, and the quantum number corresponding to angular momentum is a good quantum number. And in order to see that, we will study the rotational invariance, that is the rotation operator and when it acts on a wave function, etc., and how it relates to the Hamiltonian of the system. So, let us try to define angular momentum in spherical polar coordinates, and we will see that in just a while, that this is purely a function of the angular variables, namely theta and phi. We know that the x coordinate in the Cartesian coordinate system, x, y and z coordinates, they are written in terms of r theta and phi as this: x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta, and r square equal to x square plus y square plus z square. This is known. This is the norm of the vector, or the rather the magnitude of the vector. Cos theta is given by z by r, which that defines theta, which is equal to cos inverse. So, that tells that theta is equal to cos inverse z by r, and of course, tan phi equal to y by x, which says that phi equal to tan inverse y by x, and these are the interrelationships between the variables in Cartesian coordinate and the spherical polar coordinates. This I do without a proof. The definition of L is equal to r cross p. So, where p is equal to minus I h cross a del operator, which can be written as I cap del x plus j cap del y and k cap del z, and r can be written as like this. And when we change it to the spherical polar coordinates, it is seen that they are purely functions of theta and phi, just what I told a while back. So, L x is equal to I h cross sin phi del theta plus cot theta cos phi del phi, L y equal to I h cross minus cos phi del theta plus cot theta sin phi del phi, and L z, which has the simplest form, which is minus I h cross del phi. Now, these the proofs you can easily do it yourself, or any book on quantum mechanics which discusses angular momentum will give you these expressions. So, L square, which is the square of the components, sum of the components, which is L x square plus L y square plus L z square, has a form minus 1 over sin square theta del 2 del phi 2 plus 1 by sin theta del theta of sin theta del theta, and acting on a function. Now, it is worth mentioning here that most of you are familiar with the hydrogen atom problem, which is a problem is a 3-dimensional problem, where there is one electron in the outermost shell, and there is a nucleus at the, there is just one shell there, and there is a nucleus at the center of the atom, and the nucleus contains a proton. So, the proton and the electron, they are interacting via Coulomb term, Coulomb repulsion, or rather Coulomb attraction here, because of opposite charges being involved in this particular case. And if you write down the Schrodinger equation for a hydrogen atom, you will have the first term, which is the kinetic energy term, involves minus h square by 2 m d2 del square term, and this del square term contains a del r square and a del theta phi square, and incidentally this del theta phi square exactly apart from a small factor, that is a constant factor, is exactly this term, this angular dependence that is written. So, which means that the eigenfunction or the angular eigenfunction of the hydrogen atom problem coincides with the eigenfunction of the L square operator, and hence things becomes easier, and which we know as called as spherical harmonics. So, only we are left to solve this, which are then obtained in terms of these log-ware polynomials. So, those things are known to you when you had gone through the first course of quantum mechanics. So, just to make you aware that this is the same as this term that we have found in your quantum mechanics or rather this hydrogen atom problem. All right. So, so there are commutation relations. In fact, the L operators, the components of the L operators do not commute with each other, and they have a commutation relation which is in the most compact form is written as L cross L equal to I h cross L. So, that means that there is a L I L j, this is equal to I h cross epsilon I j k L k, where epsilon I j k is a Levi-Civita tensor, it is a symbol which takes a value 1 when you have I, j and k to be it is taken in a sort of a sequential manner, and if you interchange the, or rather if you break the sequence, then it brings up a negative sign. So, this tells that, so there is a Lx and Ly, so that is equal to I h cross Lz, and that is a commutation relation. Now, if I take a Ly and Lx, that of course will bring me minus sign that comes here. Similarly, L square, the square of the angular momentum operator, that of course commutes with all of these components Lx, Ly and Lz. So, they have similar or rather same simultaneous eigenfunctions, which means that L square and any component of L has same or simultaneous eigenfunctions, that is same eigenfunctions, and so and they can be diagonalized simultaneously. However, in most practical cases, two operators are chosen, that is L square and Lz, for no particular reason other than the fact that Lz has got a particularly simple form and Z is often taken as the preferred axis. And the angular momentum operator depend only on the angular coordinates, which is what we said. So, any radial function f of r that commutes with any component of L. So, f of r and Lx or Ly or Lz will give you 0, and same as f r commuting with L square. So, these are things that simplify discussion concerning the angular momentum. All right. So, let us now see that the relationship between the orbital angular momentum and spatial rotations, the rotations that happen in space. So, in an isolated system is in general invariant under rotation, and let u r be a rotation operator. Okay. So, u r is an operator that rotates a wave function, and we will see that r is another operator that does a rotation on the variables. So, u r is particularly reserved for the wave function. So, u r acting on a psi will transform it to psi prime. Okay. And rotation is of course a unitary operation, which means that u r dagger u r equal to u r dagger, and that should give equal to 1. 1 means this is an identity matrix. So, now let us see the overlap of the psi prime with itself, which means that we are talking about the probability density. So, it is a psi inner product of psi prime and psi prime. Each of these are written as u r psi and u r psi. So, I can take this on the other side and write psi and u r dagger u r, and which is and this is a psi again, and which gives me, because u r dagger u r equal to 1, it gives psi psi, which means the norm or the probability density that remains conserved, whether you take it in a rotated system or you take it in the original system which has not been rotated. So, for an arbitrary operator, now let us talk about an operator or an observable A prime, which when the rotation operator acts on the observable. So, u r actually corresponds to rotation of both wave function and the observable or the operator. So, A prime becomes u r A. Now, you see the expectation value is supposed to remain same whether you have done a rotation or not, because expectation value is a physically observable quantity. So, if I take the expectation value of A prime between the rotated states, this should be rotated states. So, this is equal to I have left it simply equal to the A prime, I have left it same, but I have written that psi prime to be equal to psi and u r dagger, and there is a u r psi. Since these are same, the operator A is equal to u r dagger A prime u r, or the rotated operator A prime becomes u r A u r dagger, where u r is the rotation operator. So, this is how formally rotation is done on a system. So, we have done it on the wave function, and we have done it on any arbitrary operator, as it is easily understandable that the arbitrary operator could as well be the Hamiltonian of the system. So, we know how to rotate or rather perform a rotation operation on the wave function and an operator. So, as just as I was saying that if A is same as the Hamiltonian of the system, then we have a relation that the H prime, that is the Hamiltonian in the rotated frame, is equal to u r H u r dagger, which is equal to u r which is equal to H, and this tells us that u r H is equal to H u r. So, which means that the u r commutes with the Hamiltonian of the system, and so if this happens, then u r and H have simultaneous eigenfunctions. So, H is the Hamiltonian of a system which of course has a rotational invariance, but however, to solve for H, or rather to find the eigenfunctions and eigenvalues of H, you may have to solve a complicated differential equation by some method, which is usually a power series method. But instead of that, suppose we try to find the u r, because u r is an operator that commutes with H. So, they will have simultaneous eigenfunctions. So, if we can avoid the complexity of solving a complicated differential equation in lieu of finding a form for this unitary operator, that is worth of an exercise. So, let us consider a wave function psi of r. So, under rotation, it becomes psi prime r prime. Now, remember that psi prime is being operated. So, psi prime one gets it by operating, so you are operating on psi, and r prime one gets it, which are the variables of this for this particular problem. It is the rotation operator is acting, the r is acting on the variable r or the vector r, and gives me a new vector which is r prime. So, that is this r prime. Now, of course, what we have said earlier is true, that is the overlap or the inner product should be conserved. So, which means that a psi prime r prime should be psi of r. They could at the most differ by a phase factor. This is understandable because a norm is conserved even if psi prime and psi they differ by a phase factor, because that phase factor will cancel out, because you will take a exponential I alpha and then exponential minus I alpha, that will cancel out. Okay. So, and of course, also that psi prime of r is u r psi of r. So, this has been given by our earlier definition. So, now let us look at psi prime r prime, which is equal to psi prime r capital R, which is a rotation operator on the variables acting on r, and of course, an inverse rotation operator acting on the new variables r prime, that is the same thing. So, if you just take simply the first part and the last part, so we will have a psi prime r prime that is equal to psi r inverse r prime. Now, since this acts for any r prime is arbitrary, so we can simply write it as psi prime r equal to psi r inverse r. So, since this r prime is dummy, we might as well write it as r, and this is what is written, that psi prime of r equal to psi r inverse r. This is what appears here, and the psi prime of r, which is equal to u r psi r, which is by our definition that is written here, and that is equal to psi r inverse r. So, a psi prime r is equal to psi r inverse r. So, these give you the relationship between the wave functions after rotation, or the rotated wave function versus the original wave function. Now, let us discuss something called infinitesimal rotations, and the reason that we do it is the following, that usually rotations do not commute. So, successive rotations do not commute. What we mean to say is that if we rotate a quantity, or rather rotate an object, suppose this is the object that we want to rotate, and this is the z axis that is passing through this. So, if you rotate it about the z axis by an angle 90 degree, and then we rotate it like this, okay, and instead of that, if we first, so this rotation, so this is my x axis, and this is my y axis, and this is my z axis. So, we have done first a rotation through the z axis, and now I will do a rotation about the y axis. So, it takes a form like this. So, the white part of the duster, which is this one, is towards me, and the black part of the duster is facing you. But however, if we do it, so we first do it rotation about z axis, y axis. So, that is your y axis. So, this is this is your y axis. So, we take we do a rotation about this, and then we do a rotation about the z axis, which is this. Then of course, the final configuration of the duster do not remain same, and hence the successive rotations do not commute. And in order to see that, we can talk about initially infinitesimal rotations, and see that actually infinitesimal rotations by an amount delta alpha, where delta alpha is very small, that commutes. And let us do a rotation by an angle delta alpha to a system in a positive direction, or it is a right handed sense. So, if you do a right handed rotation about z axis, so it rotates anti-clockwise, and this is represented by a u z delta alpha. U z is a rotation operator, delta alpha signifies that it is a rotation about by an angle delta alpha. So, to the first order in delta alpha, which means that if delta alpha is small, the coordinates x prime, y prime and z prime of the r prime vector, which is equal to r r, which a capital R operating on small r. So, x prime becomes x minus y delta alpha, and x y prime becomes x y plus x delta alpha. You should convince yourself, and z prime equal to z because we have rotated it about the z axis. So, z coordinate remains the same, and in general this you might have learnt in your classical mechanics course, that r prime or the variable, the rotated variable, is related to the original variable before rotation by this r plus this angle delta alpha, and this n cap is the axis about which the rotation has taken place, crossed with r. So, here delta alpha is of course delta alpha itself, n cap is z cap. So, it is a z cap cross r. So, so x prime will be x plus delta alpha z cap cross r, and similarly y cap equal to y y plus delta alpha z cap cross y, y component. I mean r means x component, y component and z component, and you will see that because z cross z equal to 0. So, that is, so z prime becomes equal to z, and these other things will remain will be written as something like this. And of course, you get a minus sign because you get a z cap cross x, which is x cap. Okay. So, r, if you just simply write it with x cap plus y cap plus z cap, you would get, and apply this, you would get these relations between the rotated variables and the original variables. So, the coordinates of r inverse r are obtained by changing. So, now I am doing it, now here I have done it with rotating it by r. If we rotate it by r inverse, that can be obtained by simply changing delta to minus delta alpha to minus delta alpha, and your psi prime, which is a rotated wave function, psi prime of r is u z delta alpha psi of r, and by our earlier definition this is equal to psi r inverse r, and we have simply changed the signs in between. So, it became x plus y delta alpha and x delta alpha minus y and z. So, doing a Taylor expansion and retaining terms till first order in delta alpha, one can find that u z delta alpha, that is this thing, is x y z. So, doing a Taylor expansion of this. So, this is y delta alpha del psi del x and minus x delta alpha del psi del y. Just to remind you that a function f of x is done a Taylor expansion about some x 0, this is equal to x minus x 0 f prime evaluated, f prime of x evaluated at x 0, and so on. And then there are terms which are of the order of this x minus x 0 whole square, and that is what we have done here. So, if you do a bit of simplification, it becomes 1 minus delta alpha x del del y minus y del del x and psi of r. So, if you remember that h cross x del del y minus y del del x, that is the definition of I L z, which simply comes from L z equal to r cross p and the z component of that, where x equal to x x cap, y cap, z cap, and p is equal to minus I h cross del del x x cap minus plus del del y cap and del del z cap, and then you take the cross of that. So, u z of delta alpha, which is here can now be written as, it is equal to u z delta alpha psi of r equal to 1 minus I by h cross delta alpha L z, and there is a psi of r which is psi prime r prime. So, the operator u z delta alpha is equal to 1 minus I by h cross delta alpha L z. So, this is the form of the operator, this is what we were trying to find, because just to remind you that that u r or here u z commutes with h. So, they have simultaneous eigenfunctions. So, instead of solving for h, we are solving for rather trying to find a form for u r, which is u z here, and similarly u y delta alpha is equal to this and u x delta alpha is equal to this. So, it is very clear that the u y goes with L y, u x goes with L x, and u z goes with L z. So, u n cap, where n cap is an arbitrary axis about which the rotation takes place by an angle delta alpha, is equal to 1 minus I by h cross delta alpha n cap dot L. It is almost clear from this part that if we have included a term which is quadratic in delta alpha, we would have gotten a delta alpha square by 2 factorial and then all these things square. And so, all these terms or the parts of the series which is exponential minus I and so on, which is what we are going to see. So, it is exponential minus I alpha n dot L, that is a part of the series, but we will see that clearly later. Thus, L is called as the generator for infinitesimal rotations. So, it is a generator for rotations. and which means that if some operator commutes with uz or un cap or ur, it also commutes with all components of L. However, the components of L do not commute amongst themselves. So, in general, rotation operators do not commute unless it is done about the same axis. This is what we have demonstrated and explained as well. So, now it must be pretty clear that the non-commutability in rotation is due to the non-commutability of the components of the angular momentum. Okay. So, because the different components of angular momentum do not commute, so the rotations about different axes they do not commute. However, this is untrue at least for infinitesimal rotation. Let us check this. So, we have r prime equal to r r. So, r plus delta alpha n cap cross r, uy delta alpha ux delta alpha psi of r minus delta alpha y cap cross r, which is delta alpha x cap cross r minus delta alpha. So, this is that second rotation. So, I am trying to find a commutation between uy delta alpha and ux delta alpha. So, I reverse the order. So, which is ux delta alpha uy delta alpha acting on a psi of r, and then everything is same excepting that you change your y by r, and now you take the difference between the two, that will give me the commutation of ux delta alpha uy delta alpha and psi of r. Now, this is so this the second term minus the first term, and this can be, the bracket can be opened and some simplifications can be done, and once you keep following these steps, is very straightforward. If you follow the steps, it becomes equal to delta alpha square I by h cross L z psi of r. So, this commutation has only non-zero values up till order delta alpha square. So, if delta alpha is small, delta alpha square, if that can be neglected, then this is equal to 0. And this thing can be, I mean, since it came out as Lz, if you follow this simple few steps, so this is equal to Lx Ly commutation, and this is equal to the commutation of Lx Ly and so on, and that is equal to 0 if we ignore terms of the order of delta alpha square. So, infinitesimal rotations commute, but not the finite rotations. Okay. And as I told you earlier, that the finite rotations do not commute because they have the components of the angular momentum do not commute amongst themselves. So, let us go to the finite rotations then, because infinitesimal rotations are really idealized concepts. But however, you can build up finite rotations starting from a large number of infinitesimal rotations. So, finite rotations by an angle alpha can be defined as un alpha plus delta alpha, which is un alpha and then un alpha. So, now this of course, you can write it in any order you want, because it is a rotation about the same axis. So, the finite rotation along any arbitrary unit vector n cap can be built up by successive infinitesimal rotations about that axis, and un cap alpha plus delta alpha equal to 1 minus I by h cross delta alpha n cap dot L and un alpha. Now, if I do this, so dun, which is equal to un cap alpha plus delta alpha and un alpha, this becomes equal to this. And if I do the simplification, I get a differential equation which is for the rotation operator, which is du n cap alpha by d alpha is equal to this, and then if we integrate, you get un alpha is equal to exponential minus I h cross alpha n cap dot L. This is what I was saying, that the expression that we got here is actually the limiting expression for this one as a exponential. So, if you expand the exponential, the first two terms you will get it as 1 minus that term that was written, which is delta alpha in cap dot L. So, if a system is invariant under rotation, finally we get that the u r and h would commute, and since angular momentum is a generator for infinitesimal rotation, it follows that L commutes with H and also L square commute with H, and they have the same set of eigenfunctions. So, we will see examples or applications of this rotational invariance of systems. I am sure that you have studied hydrogen atom, which is as I said, that it's the simplest atom with one electron and one proton, and you have solved the Schrodinger equation for that. And luckily, because of this relation, we did not really have to solve the theta phi part of the angular part of the Hamiltonian, which coincided exactly with apart from a constant factor with L square, and that is why they had the same set of eigenfunctions, which are known to be the YLM functions or the spherical harmonics.